y1, because this is also y1, because they're equally spaced. So this is just twice y1, or twice lambda r over d, which corresponds to m equals 2. And then if you want to know this one here, the height from the central bright maximum to the third order maximum, that's y3, and that's going to be 3y1, because this is also y1 over here. So y3 is just y1 plus y1 plus y1, or y1 times 3. This is just a shorthand notation to tell you that they're all equally spaced and what the separation distance is on the screen, right, of two adjacent bright spots. But as I showed you in class the other day, if you see a picture of this on a screen, it's very symmetric. So the distance between adjacent dark spots, like between this dark and this dark, is the same as y1. And the distance between this bright and this bright is the same as y1. Okay? So, but if you want to obtain an expression for the dark spots, let's say y dark, then what is that going to be? Well, the first one over here will be what? That will be half of y1, correct? So that'll be half of y1, which will be 1/2 of lambda r over d, because y1 is lambda r over d. Now, what about for this one? The height will be all of this. And that height will be what? It'll be half of y1 plus y1, because the distance between two adjacent dark spots is y1. So it will be, well, y1 for the maximum. So it will be half plus y1. So this will be 3/2 y1, or 3/2. And that y1 is for the bright ones, 3/2 lambda r over d. So in general, you can write this as m plus a half. I like to call it prime, m prime, and then lambda r over d. And for both of these, where m is 0, 1, 2, 3, 4. And the same thing for m prime, 0, 1, 2, 3, 4, and so on. Notice that if I choose m equals 0, I get that height to the first dark above the central bright maximum. So this one here, this one, I'll just do it on this side because it'll be, this is m prime equals 0. So it's the first dark, but it corresponds to m prime equals 0, not 1. And then this one, this other dark over here, this is when m prime is equal to 1. But it's the second dark, right, from the central bright maximum. This other dark one here is m prime equals 2. This other dark one is m prime equals 3. So anyway, this is really what we need to know. And then you can have various questions where they tell you the location of a bright spot or a dark spot, and they'll say it's a second order maximum, or it's the second bright spot, dark spot above. And then you just use the geometry to figure out various questions. And if the question is this, if you consider this spot over here, if you consider this spot, this one, this bright, and light makes it there after going through these two slits. So that the light coming over here of wavelength lambda comes through the two slits, and then they go from the slits to that point, and then they interfere. And if I ask you, what is the path length difference between the wave that went, what is the path length difference between the wave that went from here to there and the one that went from here to there? So that for that particular question, what is the path length difference? So I call it delta. So it'd be r, like R2 minus R1, is the extra distance that one wave travels relative to the other one. What's the answer for that one? Does anyone remember? What are the conditions for bright spots for the path length difference. What's the condition for bright spots?
Be in phase.
What's that?
They have to be in phase.
So they are in phase, so it'll give you a bright spot. So what's the formula? What is the condition that has to be satisfied?
0 lambda.
M times lambda, right? Well, what is M? What's the value of M? I asked you this point. What's the value of M over there? 1. So what's the path length difference? Just one wavelength. In other words, if the wave that went from here to there traveled 10 wavelengths, the one that went from here to there will have traveled 11 wavelengths. Longer because it's, you can see it's a longer distance. Yes? What if I ask you, what is the path length difference for this spot over here? That is, if you consider the light that went this way to that spot and the light that went this way to that spot, and it gave me a bright, right? So they are in phase when they get there. So what is the path length difference for that one right there? 4 times lambda. So that if this distance over here is, for example, 12 lambda, the distance that the other wave traveled must have been 16 lambda. So, you have expressions like this, but don't just memorize them, think about what they mean, so that then a question that may sound like a difficult question is really an easy question.
Wait, shoot.
Yes, question?
I was a little confused when where did 12 and 6. I know it's an example, but how did we get 12 and 16 lambda again?
I just made it up.
Okay.
But what do you notice about 12 lambda and 16 lambda? By how much do those distances differ?
By 4.
And that's what this is. This is the length traveled by one wave minus the length traveled by the other wave.
Oh.
But if one wave travels an extra distance of 4 wavelengths, when they arrive, they'll arrive in phase. Assuming they, of course, started in phase also, right? And that's why we take light from the same source. So you said that the two sources are coherent. Yes? So it's a conceptual question. What is the path length difference if I consider, for example, this point? If I tell you that the distance traveled by this way from here to there is, suppose I tell you that to go from here to there is 13 lambda. I'm just making it up, right? What is the distance traveled by this wave that went over there? What should this distance be?
15 lambda?
How much?
15? No?
No, because if this is 15 lambda, what will be the difference between these two?
So would it be 11 lambda?
It will be,
Oh, wait, sorry, 2 lambda?
huh?
Oh, wait.
No. So suppose you say it's 15 lambda, right?
Mm-hmm.
What's the difference in the distances traveled by these two waves?
2 lambda.
Negative 2 lambda.
And 2 lambda will give me a bright spot, but that's a dark. So what should this distance be?
5 halves.
Huh?
8 over 2.
Well, that's the difference. So therefore, what should this distance be? What should this distance be?
15.5.
Is there another possible answer?
10.5.
Now look at the picture. Which do you think? Which of these two distances is longer? The top one, right? So if that's 13, so the other one has to be, yes, one of these two, but the shorter one. Well, not one of them, but the shorter one of these two is what it should be, right? So then this has to be 10.5. Because the path length difference for this one, for the dark spots, right? I don't know if you want to call it delta prime. It would have to be m plus a half lambda. And in fact, m prime. So notice, this is m prime equals 0, m prime equals 1, m prime equals 2. 2 plus 0.5, 2.5 lambda. So if this one travels 13 wavelengths, Right? This one must have traveled, well, 2.5 wavelengths shorter. So they will be, oh, not just 10.5, 10.5 lambda is what I meant to write. Yes? Okay, so I mean, you know, there are formulas like this, and you say, okay, this is for the dark spots, right? So this is dark. So know what that means, what it represents. It's the extra distance that one wave has traveled relative to the other one. And, you know, and then this one, this is for the bright. Yes? Anyone confused? No? So, you know, if I give you if in the next test I ask you a question like that, okay, suppose the distance traveled from this slit to that slit is blah, blah, blah. What's the distance traveled the other way? That went through the other slit to that same point. So, okay.
When will our next test be?
After chapter 30, this is 35?
Yeah.
So after 36. Okay, the next topic